Greetings, scholars. I hope you're well. I hope you're safe. Wanted to get on to record a lecture for the remainder of chapter 9. So what we'll do for this week, I'll post this lecture this evening. You'll have it for the rest of chapter 9, and then we'll move into the chapter 10 on Wednesday. So many of you know there was a warning for active shooter on campus. So many of us didn't attend class, which is okay. So what I'll do for our safety is I'll post a video kind of going over a few examples in chapter 9, highlighting effect size measures that you'll need to know. And then we'll move on and transition into chapter 10 Wednesday. So that'll be how we'll move forward. Many of you have attempted the homework for chapter 9 and have also worked on the practice problem. So what I'll do, I will extend the due date for the homework till Friday, and then you'll also have some opportunities to complete the rest of the practice problems. I've also posted the answers for those, so please get those submitted. I need to see your work, how you worked out the problems. Even though you have the answers, you still be able to work those problems out. So that'll be useful for the exam that we'll have coming up in a couple of weeks. So again, bear with me. We're going to walk through a couple of examples. I'm going to review the example that we talked about. We talked about t-tests for the example that we used for before spring break. So you get an idea of where we are, and then we'll use that same example to evaluate and calculate the effect size measures for those problems. Okay. So let me share my screen so you can see. Slides that I'll be using. Okay, so we began to talk about the hypothesis test. And one thing that separates the t-test from the z-test that we learned in chapter 8 is we do not know the standard deviation for the population. And so since we do not know the population standard deviation, we're going to estimate that standard deviation. So now what we'll be calculating is the estimated standard error. And by calculating the estimated standard error, now we'll be able to calculate and compute the t-statistic, which is very, very similar to what we did for the z-statistic. We'll be using our table I passed out in class, and that table will allow us to identify the different critical t-values that we're using to make our decision, whether or not to reject the null hypothesis or fail to reject the null hypothesis, okay? So again, this is what we'll be doing. This is kind of conceptually what we'll be doing for chapter 9 and moving into chapter 10. So you have a known population before treatment. So you know your mean, okay? Usually let me go back. So you know your mean here, but you don't know the standard deviation, okay? And oftentimes when you think about research that is done in the real world, especially for social research, social science research, behavioral research, you don't know a lot about the population. You may know the population mean, but you won't know the standard deviation for the mean or for the population. So what we'd have to do as a researcher is then estimate the parameters for the population. So in this particular instance, you do not know the standard deviation. So that's the one thing that we'll be doing is having to estimate the population standard deviation. I'll show you how to do that. Okay, so you have your treatment, and then you'll have the unknown population after treatment. So in your research, for researchers that are working in the real world, you won't know the population standard deviation, and you won't know the population mean after the treatment. So you have to use your sample in order to estimate those values. You're going to be estimating the population value using a sample, and you're going to be using a sample standard deviation. And so we start talking about confidence. Again, since we do not know the population mean after the population is treated, then we'll have to estimate that as well. And so we'll talk about that as we move forward. All right. The steps that we talked about, those steps for hypothesis testing are all the same. You're going to state your null hypothesis, your alternative hypothesis. You're going to select your alpha level. You're going to locate your critical region using the t distribution. You're going to calculate your t statistic, and then you're going to make a decision regarding the null hypothesis. Either reject the null hypothesis or fail to reject the null hypothesis. Okay. Here is the example that we used before spring break. Okay, so it says Chang, Ashbach, Duffy, and Scheisler report that reading from a light-emitting e-reader before bedtime can significantly affect sleep and lower alertness the next morning. So to test this finding, a researcher obtains a sample of n equals 9 volunteers who agree to spend at least 15 minutes using the e-reader during the hour before sleeping and then take a standardized cognitive alertness test the next morning. So they're measuring alertness the next morning. For the general population, scores on the test average a mean of 50 and form a normal distribution. It says the sample of research participants had an average score of a mean of 46 with a sum of squares equal to 162. It says we will set the level of significance at an alpha of 5% for a two-tailed test. Okay, so what I'm going to do is I'm going to walk through these very briefly. And as we walk through these, I'm going to show you why we need to identify the different areas of this problem, right? It's a lot of information, but we're going to take out all the relevant information, and then we're going to solve for the problem, okay? So let me stop sharing the screen. If you need to pause, we're going to go back to this, and then I'm going to identify the different areas that are needed for this particular example. Okay, so very important that you identify the information that you need so that as we solve the problem, you don't have to go back and forth with the problem. You already have it written out based on what you need. Okay, and we're going to solve this using the hypothesis testing procedure. We're going to go through step 1, step 2, step 3, and step 4, and then I'll show you how to calculate the effect size measures for this particular problem. Okay, let me stop sharing my screen. And I'm also going to remove the blur from the background. All right, so you're going to need your sheet. Okay, you're going to need your t distribution sheet. This is going to give us the opportunity to look for the t using our degrees of freedom and our alpha levels. We'll be able to identify what the critical t value is for our problem. Okay, so let me share my screen, whiteboard, and then we'll get started. Okay, so let me go here. All right. Do this my collaborating. All right. So let's go ahead and work through this so you can see my screen. Okay. Go back to my whiteboard. Share whiteboard. All right. This really quickly. Sorry for the okay. So let's do this. Okay. So this is the information we have. Go to mom. All right. So it says these researchers report that reading from an uh, a light emitting e-reader before bedtime can significantly affect sleep and lower the alertness the next morning. So it says to test this finding, a researcher obtains a sample of N. Let me go here. N equals non-volunteers, and those volunteers spend at least 15 minutes reading an e-reader during the hour before sleeping. And then they take a standardized cognitive alertness test the next morning. Okay. The population that uses the e-reader, okay, they have a mean of 50. Okay. So these are individuals who there's alertness test and they're not using the e-reader at all. And then you have the individuals who actually use the e-reader and they have a mean of 46 and a sums of squares of 162. Okay. So there's going to be two things that we have to do. We're going to have to find our estimated standard error or the standard deviation for our sample. And then once we find that standard deviation for our sample, then we'll be able to calculate a lot of the other things. Okay. The other thing that we'll need is our degrees of freedom. So our degrees of freedom for this particular research is going to be n minus 1, or degrees of freedom equals 9 minus 1 equals 8, right? So our degrees of freedom equal 8. We're going to be using this in order to identify what the critical value is for our t value, okay? So step one for hypothesis testing, okay? You have to identify your null hypothesis and your alternative hypothesis, okay? So our null hypothesis for our research is going to be our mean equals 50, okay? That means that there is no difference between the population and the treated population that reads the e-reader at least 15 minutes before they go to bed, okay? Then you also have your mean, which is not equal to 50. So this means that there is a significant difference, right? There's going to be a difference in those values, right? So there is a difference between the population that does not reading the e-reader and the population that does read it, okay? That's step one. And then you're also going to select your alpha level, which is an alpha or significance level of 0.05 or 5%. Okay, so we have our alpha level and we have our hypothesis test, right? So we have our null hypothesis, the hypothesis for that, and we have an alternative hypothesis. The next thing is we have to calculate our critical value, right? So given our information, we know that we have a degree of freedom of 8. We know we have an alpha level of 0.05, and we know that it is a two-tailed test. So two tails, all right? So on our sheet, we know that we're gonna go to two tails, 5%, and our critical T, you're gonna go over to degree of freedom of 8. You're gonna go over to where that intersection of the 5% or 0.05 for two tails, and you should get a critical T of 2.306, and that's gonna be plus or minus 2.306, right? So given that information, I know that's my critical value, right? That's step two. Step three is I have to compute my statistics, all right? So let me scroll back up because, again, like I talked about before, I need to identify my sums of squares, all right? So my sums of squares is 162, and so I'm going to be using that in order to identify my statistic, right? So the first thing I need to do first is I have to calculate my standard error, my standard error of the mean. So the first thing I'm going to use is my sums of squares equals 162. I have to find my, and this is my estimated standard error of the mean. It's going to be S equals the square root over the square root of n, okay? So this is what I need. I need to find this value right here, okay? And so the way I find that is I take my degrees of freedom here, and I have to find my variance. The way I calculate my variance is sum of the squares divided by degrees of freedom, okay? So you should get 162 divided by 8. So if you do the math, 162 divided by 8 gives you 20.25, okay? But now I'm not just looking for my variance, I have to look for my standard deviation. So I want to take the square root. Yep, I'm going to take the square root of 20.25. That's how you find your standard deviation. And you should get 4.5. Okay, so you should get 4.5. All right, so now I have everything I need. This is what I needed to get my estimated standard error. So let me slide down here so you can see that. Okay, the next thing I need to do, all right, is find my standard error of the mean. So my estimated standard error is going to be 4.5 divided by the square root of n, right? I know my degrees of freedom are 8, right? So then I know my n should be 9, right? So 8 plus 1 gives me 9, which is my n, okay? So let's solve this out. It's going to be 4.5 divided by square root of 9 is 3. So estimated standard error, 4.5 divided by 3 should give you 1.5. All right. So now, great. Now I have this value. So in order to find my t is going to be my mean minus my population mean divided by standard error of the mean, or estimated standard error of the mean. Okay. Given this information, I'm just plugging in values now. So if I go back up, my population mean is 50, my sample mean is 46, and so let me go ahead and write this out. Given the information, I know my sample mean is 46, my population mean is 50, and my estimated standard error of the mean is 1.5. Okay, so now I'm just going to plug values in for my t. It's going to be 46 minus 50 over 1.5. Okay, so a -4 divided by 1.5 gives you a negative 2.67. All right. All right. Given this information, right? Given this information, I'm going to slide down and make my decision, right? So my decision should be, I have my t value, critical t equals 2.306. My t value, actual t value that I got was -2, and it's plus or minus 267, right? So to make a decision, I got to compare this value to this value. So since this value is less than -2.306, I'm going to reject the null hypothesis. Okay, that means that there is a significant difference between those individuals in the sample who read an e-reader for at least 15 minutes before bedtime and their level of alertness to those who did not, right? So after giving those individuals that treatment, I realize now that that e-reader does play a big role in affecting the alertness the morning after the person has read at 15 minutes, or at least at 15 minutes before bedtime, an hour before bed. So again, we know that the e-reader is playing a big difference in what's happening with the alertness of the individual the next morning. Okay. All right. So let me stop sharing. Let's go back. Stop sharing this. And let's go back to our slides. And again, pause if you need to in order to identify those different areas. But again, that is how we're going to be using our t-test, right? Hypothesis testing procedure. All right. So that is we reject the no hypothesis for this example. All right. So those are our 4 steps. So again, this is looking at our shaded region. So our value that we got was negative 2.67. So that negative 2.67 will lie in this area here. And so that means you're rejecting no hypothesis. Had that been anywhere in this region, then you would fail to reject, okay? So again, these are the assumptions that we made. Again, the value of the sample must consist of independent observation, and the population sample must be normal. Again, we talked about this the week before spring break. All right. The larger the sample, the smaller the error, and the larger the sample, the greater the likelihood that you're going to reject your null hypothesis. Okay. The larger your variance, the larger the error. And so if you have a large variance, then the likelihood that you're going to reject the null hypothesis also reduces. Okay. So you're going to reduce the likelihood of rejecting the null hypothesis when you have a very, very large variance. But when you have a larger sample, you will, again, have a smaller error, which then increases the likelihood of rejecting the null hypothesis, okay? So it says when the n is small, less than 30, the t-distribution is blank, right? So we talked through this on the week before, and you should have selected B. So it should be flatter, and it should be more spread out. As you increase your value for t, right, that value becomes more and more like the normal distribution. As you decrease the value for t, if it's smaller than 30, then it's going to be more flat, and it's going to be more spread out. You have more variance, more variability. But as you increase the value of your n, you're going to decrease your standard error, decrease your variability, which then, again, it makes it looks more like the standard deviation that we get for a normal distribution. All right. So it says by chance, 2 samples selected from the same population have the same size, n equals 36, and the same mean. That means that they also have the same t-statistic. We talked about this before. That is going to be false because the variability in these samples might be different. And so since the variability of those samples might be different, then your t-statistic will also likely be different. Even though they have the same mean and the same sample size, they might have different variability or standard error, which means that you might have a different t, which again makes the t a little bit different. So it says for the second one, compared to a z-score, a hypothesis test with a t-statistic requires less information about the population, right? That is true, okay? So the first one is false. The second one is true because the t-statistic does require less information, right? You don't have to know the population standard deviation, so it requires less information to compute your t-statistic. All right. All right. Effect size, right? So it says measuring the effect size for the t-statistic. We're going to go through this pretty quickly. A lot of this is what we talked about already. The t-statistic is not that much different than the z-score, the z-test. We'll just talk about how you calculate, right? So when a value is considered significant, right, we know that there is a difference, right? But the effect size lets me know how big that difference is, right? And it takes out the sample size affects, how significant your value will be, right? How significant the difference is. And so with that being said, in order to remove the effect of the sample size, I want to use my Cohen's d or the effect size measure in order to see how big that difference is. What is the magnitude of that difference? Because even though there is a significant difference, because again, when you have a large sample size, that increases the likelihood of increasing the likelihood of rejecting the null hypothesis or finding something significant. So by removing the effect of the sample size, and I'm only looking at the difference in the population mean and the sample mean and the standard deviation, now I'm able to get a standardized difference, and I'm able to compare that to other samples or other research populations if I so choose to do so. Okay, so again, the chance is measured by standard error. Again, no measure of the size of the effect is included, and so a very small treatment effect can be statistically significant, right? So we want to take that out of the equation, specifically as it relates to sample size. Therefore, it says the results of a hypothesis test should be accompanied by a report of the effect size, such as Cohen's. Every time that we do an effect size measure, see we make that decision for rejecting or failing to reject the null hypothesis. You also want to have an effect size measure because it allows me to see how big that difference is. What is the magnitude of that difference? Not is there a difference, but how big is that difference? All right. So very much like we did for the z-test, the estimated Cohen's d, and we talk about the estimated Cohen's d because we're using our sample instead of our population in order to calculate the Cohen's d for this particular value, right? And by using the estimated Cohen's d, we are using the estimated value of the sample here, right? And so since we're not using the population, we're using an estimate, we call it the estimated Cohen's d or the estimated d, right? So we're using the sample standard deviation, which makes that an estimation. All right. So you have the same thing in the numerator here, the mean for the sample and the mean for the population. And the only difference now is the sample standard deviation, which again is going to give you the same things. These are the same magnitudes here, the same criteria. So anything less than a 0.2, 0.2 or less is a small effect size. Anything greater than and between a 0.5 and 0.2 is a medium or moderate effect size. And then anything larger than 0.8 is considered a large difference or a large magnitude, okay? All right, so in our example, we talked about the e-reader, the light emitting e-reader, right? So the sample had a mean of 46 with a standard deviation of 4.5, right? And so in order to conduct and collect our estimated Cohen's d, you're just gonna take the mean that we got, which was population for the mean was 50. The sample mean was 46. And you're going to divide that by 4.5. Very, very easy, very, very simple. Okay. So let's do that really quickly. All right. Let me go share my screen. All right. So given this information, I know again that my mean, actually, let me go back. I'm going to use this one. All right. So what I want to use is, again, I have my mean 46, my sample mean of 46, population mean of 50, and I have my standard deviation of 4.5. And again, small effect size. Again, remember these conventions, 0.2, medium effect size, 0.5, large effect size, 0.8, right? So now I'm just looking at the magnitude of that difference. I know that there was a significant difference between my sample mean and my population mean, but how big is that difference? I know it's significant. I know that there is a difference, but how big is it, right? So now let's look at that. So we got 46, estimated D equals 46 minus 50 over 4.5. So you should get 4 divided by 4.5, and you get a pretty small effect size, 0.22. All right. So with that being said, if it's 0.22, we see that it's a really, really small effect size. So even though there is a significant difference, the magnitude of the how big that effect is pretty small, right? And so we have to take that into account when we think about significance. We rejected the null hypothesis, but the effect size is really, really small, right? So that an e-reader really didn't play that big of a difference in the alertness. I mean, it does play a difference, but the magnitude of that difference is really, really small, okay? Let me stop sharing. Let's go back to my slides. All right. But again, you see the effect size here, right? When you have all of your scores here, right? This is a sample kind of displaced around here. I mean, it's not that big of a difference there, right? You see that there are some differences, but they're not that big of a difference because again, they're within, pretty much 4.5. But if those differences had been out here, right? If you had a lot of them that are out here in 39s, 40s, right? You might see a larger difference because now your mean or your sample mean would be very, very different. Okay. All right. So here is another example, right? It says you have a sample of n equals 16. You have a uh, population mean of 40. You have a sample mean of 44. You have a variance of 16. It says use a two-tailed test with a 5% significance level to determine whether the treatment effect is significant and compute the Cohen's d to measure the size of the treatment effect. Okay, so I'm gonna go ahead and do this. I'm gonna go ahead and walk you through this example. This is a good one to highlight. So let's go ahead and do this really quickly so you can get an idea of how this would work. Okay, let me go ahead and share my screen so you see what we do. All right, so for this one, it says you have a sample of n equals 16. All right, sample of n equals 16. You have the population mean of 40. The sample is 44. They had a value of 16 for the variance. The alpha level, I'm writing all the important information, is 5% with a two-tailed test. And then also, we have to calculate another few things. So my degrees of freedom for this, I'm going to go ahead and calculate everything that I need. Degrees of freedom for this one is 15. And I know that my critical T, I'm going to go ahead and do all this so that we can move right along, right? So I know that my degrees of freedom are 15. I know my value for my two-tailed test is going to be the value for the degree of freedom of 15 on my chart. I go over and across, and I get a T, critical T of 2.131. Okay. What else do I need to calculate? I also need to calculate my standard deviation. In order to calculate my standard deviation for this sample, I take the square root of the 16, square root of 16, square root of 16 should give you 4. Okay, so I have a standard deviation of 4. So I'm getting everything I need so that when I calculate all my values, man, I got it, right? So I know that my hypothesis test, I'm just going to go through it really quickly for you. So my hypothesis test is going to look something like this, okay? My null hypothesis and my alternative hypothesis should look like this, equals 40. My alternative hypothesis should look like this, does not equal 40 because again, we're saying that there is a difference between the sample and the population, all right? 2, okay? I'm calculating my critical T, right? I already got it here, I'm just rewriting it here. 2.131, right? Two-tailed test, that's my criteria. Now I need to compute my statistic. I'm moving pretty quick, but again, we're gonna compute my statistic now, all right? So I know that my standard error of the mean is this. And then you calculate the standard error of the mean like this. So now I'm going to calculate that. That's going to be 4 divided by square root of 16. 4 divided by 4 equals 1. So I know my T is going to be mean minus my population mean all over my estimated standard error of the mean, which should give you 44 minus 40 divided by 1, 4 should give you 4. All right. So now I have to make my decision. I have my critical T. I'm bringing it back down here so you can see is 2.131. My actual T value that I got for my research is a 4. Since this value, is greater than my critical T, I'm going to reject the null hypothesis, right? So that there is a significant difference, all right? So now I've rejected the null hypothesis. So now what do we have to do? We have to find our Cohen's D. Our estimated Cohen's D is calculated like this. Estimated D is my sample minus my population divided by the sample standard deviation, right? So we're going to get, my sample was 44 minus 40, and our standard deviation was 4. Okay. All right. So that's 4 over 4. So my estimated Cohen's D equals 1, right? If you think about the conventions, 0.2 was small, 0.5 was medium, and then zero point 0.8 is large. So with a Cohen's D of 1, it's a pretty large effect size, right? That means the magnitude of that difference is really, really large. And you can think about this in terms of your sample size. So we have a sample size in this example of 16, right? In our last example, the sample size was a little smaller, was 9, right? And so with the sample size being a little smaller, that decreased the magnitude of that difference. And so with a sample size that is larger at 16, you're increasing the sample size, the effect size, which was a pretty large effect size. All right, let me stop sharing, go back. All right, so again, you should obtain, again, T of 4, degree of freedom 15, the Cohen's D. All right, the second measure, right? When you think about your research that you're doing for your sample, another measure of effect size is called the R square. And the R square indicates the percentage of the variance that is explained by the treatment, right? So if we go back to our example with the light emitting e-readers, right? And we were looking at the effect size of those e-readers on the individuals who participated in that study. So a sample of 9 volunteers volunteered to be a part of that sample, right? And they got their alertness rate was a sample of 46. They also have a value of what was that, 50 for the normal population, those individuals who are not reading those e-readers, right? In order to explain the variability in the scores for that sample, this is the way that we do that. The higher the amount of variability that is explained means that the treatment has and is playing a significant role in the variability in the individuals that you see that are in that sample. And the larger that variability is, that means the treatment is playing a big difference in the differences in those scores. So if you think about the effect size, these are your conventions, right? If the R squared or percentage of variance that explained is only 10%, or 1%, then that's not a lot of variance to explain, and there's really not that big of an effect. If it is about 9%, that's a medium effect. But anything greater than 25% of the variance that is explained by the treatment, that means that you have a really, really high effect, right? So this is just an alternative method, and it determines how much variabilities in the scores of the sample is explained by the treatment effect, right? So if those light emitting e-readers is giving me a treatment effect of something that's really, really huge, then I know that the variance that is explained by that e-reader is really, really large, right? So let's work through an example. All right. So here is the example, right? If you think about the e-reader, right? So you have a value of 46, right, for the mean, and you have uh, a population standard deviation, excuse me, a mean of 50, right? That means there's no difference. Um, the light emitting e-reader, they haven't read it, and so their alertness is really, really high, right? So let's do an example. So this first example here, these are the scores, the original scores that includes the treatment effect. So as you can see, the e-reader, excuse me, with no effect is 50. But you see that these differences here say a big, you see a big effect here, right? So here is a treatment effect, right? You have a score of 39, you have a score of 41, you have a score of 43, 45, 46, 47, 50, 51, 52, right? What if I were to increase this value by 4, right? So I want to remove the value of their treatment effect. So when you remove it, you add 4 to everything here. So you're adding 4 to the 39. 39 gives you, again, 44. Excuse me, 43. You add 4 to 41, you get 45. You add 4 to 43, you get 47. You add 45, or excuse me, 4 to 45, you get 49, so on and so forth. So you're removing the effect of the treatment. This is with the effect. This is without the effect. And so what we're doing is we're removing the effect to see what is that magnitude, right? What is the magnitude of that effect? How much of that variance is being explained by the treatment, right? By, again, those individuals who read the e-reader at least 15 minutes before, an hour before bedtime. Right? We want to see how much variance is explained, all right? And this is how you would do it, right? This is the values that you get for the e-reader, right? This is the first one, right? There's the sum of squares for the treatment effect, and this is without the treatment in it, right? You have sum of squares of 306, right? When you, again, remove the treatment effect, right? That means you add 4 to every that average that difference of 4 to every subsequent value, right? Then you decrease the value of the sums of squares, right? So these are our square deviations. After you square deviations, then you sum them. This is the sums of squares with the treatment effect, right? This includes the treatment effect. This is when the treatment effect removed. So in the first example, you have sums of squares of 306, and then you have a sums of squares with 162. All right. So let's go and show you what that looks like. All right. So let me take a picture of this, show you a picture of this, and then I will give you how we calculate it. So let's go back here. And again, take a picture of this, pause this, write this down. This is the equation for the R square, and I'm going to show you how you do it. All right. So let me share whiteboard. I believe the value that we got for our t in our example was 267. Okay. And so if I want to calculate my R squared, like I talked about here, you got t squared, R squared equals t squared divided by t plus degrees of freedom. Okay. All right. So let's go ahead and do that real quick. Okay. So you have your t, which is going to be 2.67 squared over 2.67 squared plus my degrees of freedom for that particular case. I think it was n equals 9, so that'll be degrees of freedom, 8, so plus 8. Okay, so what you'll do is you just go ahead and do the math. 2.67, 2.67, that's 6.942. So 2.67. Oh, it's wrong. So let me go over here. Let me bring this down. Okay. So I'm going to go down here with it. So 2.67 squared, excuse me, 7.1289. So since I know that's the same thing, it'll be 7.1289 plus 8 plus 8. That's going to be 7.1289 plus over 15. Put 1289. So 7.1289 divided by 15.1289 equals 0.47%. Okay, so we saw that with the convention. 0.01 was really small effect size, 0.09 was a medium effect size, 0.25 was a large effect size. So our effect size for our e-reader, our e-reader example is 0.47. What this means is that 47% of the variance in the scores for that sample is explained by those individuals reading that e-reader. That also means that there's another 53% of the variance that is explained by something else, right? But we know that the variance explained by the e-reader itself is 47%. So 47% of the variance that we see in that sample is explained by the light emitting e-reader, right? Them reading that e-reader an hour before bedtime affects their alertness the morning after. 47% of that is explained by that. Okay. All right. So this should be or 47%. All right. Let me stop sharing. And then we'll share this again. Okay. So again, that's my convention. And like much of the same, if you were to do 162 divided by 306, so this is the treatment effect, right? This is the sum of squares for all of the treatment effect, and this is the treatment effect that's removed, right? So I'm using, let me see if I can write this out without it messing up. So if I'm doing my R squared, I'm going to do 162 divided by 306. So yeah, 306. And you should get 0.47. Okay. So again, this value gives me the treatment effect removed and the treatment effect total, right? And so that value again tells me that 47% of the value or the variance in those values is explained by the treatment effect, right? And so that's how we get that. All right. So yeah, you do 162 divided by 306. And that's about 550, yeah, about 0.52%. Right. So you get something very, very similar to what we got with the T-score. All right. Let me remove that. All right. This will be something that you'll do for yourself. Okay. So this is a practice problem. You go ahead and use this as a practice problem. You're going to use a two-tailed test. You want to go through the hypothesis testing procedure. you want to be able to compute those two different measurements of effect size. Now, I'll go through this, go over this in class, but I want you to solve this for yourself. Try this as an example. Again, all you're doing is solving for those values. You're going to solve for the Cohen's d, or the estimated Cohen's d, and you're also going to solve for the R squared. And I want you to be able to identify those as you move through, okay? I'm going to cover this in class on Wednesday, so I'll leave this for Wednesday. But I want to explain what I mean by the confidence interval, right? So when you think about confidence interval, if you go back to the beginning and when we talk about a sample, as researchers, we use estimates instead of using the actual population, because oftentimes we're unable to use the actual population to identify those different parameters. So what we do is we identify an estimate of the population using our sample, right? And so with our sample mean, we're estimating our population mean with our sample mean, and we're estimating our population standard deviation with our sample standard deviation, or estimated standard error, right? So this is another alternative technique for describing the effect size, because we are wanting to estimate an interval that contains the population standard deviation in it, right? So our population, or excuse me, our sample mean is then used as an estimate for our population, and we use our interval. It's constructed by using our estimated standard error. So I'll show you what that looks like, right? So we'll be able to confidently estimate our population mean if it's located in that interval near that statistic, right? The statistic is that sample mean, right? So if our estimated standard error is wide enough, and we are using what we call either a 95% confidence interval or a 1 or 99% confidence, those confidence intervals give me an interval that I am confident that my population standard deviation, excuse me, my population mean will be located within that interval. And that gives me a measure of effect size, because the larger that interval, so if I go 99% confident, that means I have a 1% chance of rejecting the null hypothesis, or calculating that type 1 error, excuse me, then I'm able to use that difference in order to calculate that estimate, that interval. And we'll talk about that. I'm not going to have you do this on an exam, because the more common effect sizes are going to be your R squared and your estimated Cohen's d. But you will have to do this in the homework, and you probably already have to do it. And so I'm going to show you how to do it. I'm going to give you some other attempts for the homework so you can kind of get this one down. Okay, so this is just an alternative technique in how you calculate it, and I'll show you how to calculate that on Wednesday. Okay, but here is the way that you'd construct that interval. Okay, so if I was looking at a 95% confidence interval, I'm going to use my degrees of freedom. I'm going to calculate and identify my estimated standard error. I'm also going to calculate the t that I'm going to use for that in order to calculate the value of the population that is going to fit. Where is it going to fit, right? Is it going to fit in that interval or not, right? And that'll give me the opportunity to see if that population standard deviation and mean fits within that interval that I set, okay? All right. So here is something that we did, right? So it says in the t distribution, the values pile up around the t equals 0, right? T equals 0 means that there is no difference whatsoever, right? So t equals 0, you have plus or minus to both sides, right? It goes all the way to almost into infinity, right? So what you're looking at here, you have a degree of freedom of 8, and you have a 95% confidence. That means that the values are going to fall anywhere between 2.3306 plus or minus, right? So if you're looking at your chart, you're going to go to 95% confidence interval here. You're going to go down to 8, which should give you that 2.306 plus or minus, and you're going to plug those values in, and I'll show you how to do that Wednesday. So I won't do that now. I'll put it on Wednesday. All right. But here is the distribution, right? So again, the distribution has, if your value falls anywhere in here, right? Again, in our hypothesis testing procedure, that means we're going to reject the null hypothesis, right? But we're 95% confident, right, that our value is going to fall somewhere in this shaded region, right? And that's the key, right? That's the key to this confidence interval. This is the value plus or minus 2.306. That's the confidence interval. If I were to take this to a what we call a 99% confidence interval, that means I'm going to decrease, or excuse me, increase the interval. So I'm going to go from 5% to 1%, right? And so then that goes down, excuse me. Yeah, that goes here, right? And so now I'm going to degree of freedom of 8, go over, that's 3.355, right? So then my values would be out here. So out here, let me go here, point. This will be plus. Let me look at my 3.355. Okay, and that will be minus 3. Darn, well, it's not going to work that way. Doesn't look like it's going to work for me. Let me see if I can do it one more time. If it doesn't work, then I will 3, 3, 5, 5. Okay, so now this becomes the shaded region, and this is a 99% confidence interval. Okay, so what happens is you increase the interval as you increase your confidence. That means I'm more confident, and that means that the likelihood that that population mean is going to fall within that interval is a lot greater because you're increasing the interval for that particular confidence. All right. Okay. So I'm going to show you this on Wednesday. We'll go through it really briefly, and then we'll move on to chapter 10. All right. I'm going to stop there. Again, if you have any questions, please email me. Make sure that you are able to confidently calculate your Cohen's d, estimated Cohen's d, confidently calculate the R square, and then also be able to calculate the confidence. Those are two things that are really, really important that you should know how to do. And then be able to calculate using the t-test, those hypothesis testing procedures, being able to calculate those are really important for the exam. So we're going to learn that this is a one sample t-test. We're going to learn how to calculate a two samples t-test. That means we're using two samples, two independent samples, to calculate our t-values. And we'll be able to identify the difference between those two groups. All right. So this is a one sample t-test. We'll look at a two sample t-test, and then we'll also look at a repeated measures t-test. So you'll assess a group on at one point in time, and then you'll assess them at another point in time, and then you'll compare the two values based on that single. But again, this is what we use and what we do as researchers in order to calculate the significant difference in those values. All right. All right. We'll see you all on Wednesday. Hope you all are staying safe. If you have any questions, please email me. Again, my office hours tomorrow are from 9:30 to 12:30 in the office, Carver Complex North, room 219A. So if you need anything, please stop by, or I can also meet you via Zoom. Just send me an email and I can send you the link to my Zoom link. But also the link to the Zoom is also in the syllabus. So please join in if you need to. All right. We'll talk to you later. Have a great evening.